Welcome back to QHSE Talks.
Glad to be here, as always.
So we have some intense numbers to look at today. Um, Falls account for approximately 40% of all construction-related fatalities.
Yeah, 40%.
40%, just let that sink in. And, when we look at scaffolding specifically, incidents cost the industry $90 million every single year.
Right, in medical expenses and damages alone.
Exactly. So today we have a very specific mission for you listeners out there. Whether you are, the dedicated learner, the safety professional intensely prepping for your ASP or CSP exams, or honestly, just someone who is fiercely committed to elevating the safety culture on your job site.
Absolutely. It's critical stuff for anyone on site.
It really is. So we're going fundamentally into ASP 11 Domain 2, Topic 8, Part G. We're going to master the key safety fundamentals of scaffolding.
Those statistics you mentioned, they are sobering for a reason. What's fascinating here is that this $90 million statistic directly connects to the broader picture of why OSHA's Subpart L exists in the first place.
Right. It's not just made up.
No, not at all. These regulations aren't arbitrary red tape generated in a vacuum. They are a direct engineered response to a massive ongoing loss of human life and livelihood. We are talking about literal life and death on the job site.
Okay, let's unpack this. Because when you throw out a number like 40% of all fatalities, that forces you to stop and rethink your entire approach to a construction site.
It really does. It has to.
Yeah. It means that if you are a safety professional, understanding scaffolding isn't just like a bullet point on a resume. It is arguably the most critical life-saving knowledge you can bring to a project.
100%.
So let's start by defining the actual hazard landscape we are dealing with. What exactly are scaffolds, legally speaking, and why do they fail so catastrophically?
Well, the hazard landscape really begins with how we categorize the structures themselves. And the sources break scaffolding down into three fundamental types. First, we have supported scaffolds.
Okay, supported. So that's the classic look.
Right. Exactly. These are platforms supported by rigid, load-bearing members. Think of traditional poles, legs, frames, outriggers, basically anything building vertically up from the ground or a solid structure.
Got it. Building from the bottom up.
Right. Second, we have suspended scaffolds. These are platforms suspended by ropes or other non-rigid overhead supports.
Like the window washers.
Yes, exactly. You typically see these used by window washers or exterior masons on skyscrapers hanging down from the roof.
Okay. And the third type?
Third, the regulations cover aerial lifts. This includes vehicle-mounted working platforms, cherry pickers or articulating boom trucks.
Okay, so supported builds up from the bottom, suspended hangs down from the top, and aerial lifts are the mechanical vehicle-driven boom devices. That feels pretty straightforward.
It is, yeah.
But when we look at why these structures become the site of that $90 million in damages, I have to imagine the failures aren't, mysterious anomalies.
Oh, no. They are highly predictable. The hazards generally fall into four primary categories. You've got falls from elevations, obviously.
Right.
Then scaffold collapse due to instability or overloading. Then electrocution from contacting overhead lines. And finally, struck by hazards from falling tools or debris.
Wait, falls, collapse, electrocution, struck by. For anyone studying for the ASP, you should immediately recognize how these map perfectly onto the OSHA Focus 4 hazards.
Exactly.
Falls, struck by, caught in or between, and electrocution. The Focus 4 just constantly reappear across all domains of safety.
It's because human vulnerability doesn't really change regardless of the technology we invent.
Yeah, that's a good point. But I want to zero in on the collapses and falls. It feels like we treat scaffolds as permanent, invincible parts of a building's architecture.
You really do, yeah.
Like we walk past a building under construction, we see this massive matrix of heavy steel tubes, and our brains just categorize it as a solid extension of the building.
Right, like it's made of the same stuff as the concrete foundation.
Exactly. But in reality, they are temporary modular puzzles. They were only as strong as their weakest pin or plank.
A temporary modular puzzle is the perfect way to conceptualize it. A scaffold is an intricate system under immense stress, and it's constantly subjected to shifting variables.
Like what kind of variables?
Well, you have the live loads of workers walking and moving around. You have the dead loads of bricks, mortar, heavy equipment being stacked on the decking.
Right, all that weight just sitting there.
Yeah. And then you have lateral forces.
Yeah.
Wind shear pushing against the frame. Even the continuous vibration of power tools slowly loosening components over time.
Wow, just the vibration. I have to speculate that this temporary shifting nature creates a massive psychological trap for the workers using it.
Oh, absolutely.
Because if a worker walks up the same scaffold stairs on Monday, Tuesday, and Wednesday, their brain naturally builds a habituation to it. They start to trust it, just like they trust the solid concrete stairs in their own house.
Habituation is one of the most dangerous forces on a construction site. I mean, the human brain is designed to filter out environmental threats once an environment becomes familiar.
Right. But unlike the concrete stairs in your house, the scaffold could have been drastically altered overnight without anyone noticing.
Exactly. A different trade might have come through and removed a vital diagonal cross brace just to fit a material cart through a tight
Oh,
space.
man, yeah. Or like a severe rainstorm might have washed out the soil under the base plates.
Right. And if workers trust the structure too much without verifying its safety daily, well, that psychological comfort becomes a lethal trap.
So this raises an important question regarding how we combat that exact psychological trap. Because you cannot rely on the general workforce to constantly self-police the structural integrity of a complex modular system.
No, you can't. The physical environment is way too dynamic.
Right. This is why OSHA mandates a highly structured, authoritative system of human oversight. You can't just have 20 workers with wrenches unilaterally deciding how to build and maintain a 70-foot tower.
Exactly. There must be specific roles designated to oversee this puzzle.
Which brings us right into the hierarchy of scaffold management. And honestly, this is an area where I see people get completely tangled up in the terminology.
It happens all the time.
The regulations define 3 critical roles, right? The competent person, the qualified person, and the scaffold engineer.
Yes, those 3.
But in everyday conversational English, competent and qualified sound identical. Like if I'm hiring an accountant, I want someone competent and I want someone qualified. They're used as synonyms.
They are. Yeah.
So if I'm sitting down to take the ASP exam, how do I keep from mixing these up? What is the actual practical difference?
It is the single most common stumbling block for safety professionals, but the distinction is absolute and legally binding. Let's dissect them. Qualified is entirely about brains, design, and theoretical capability.
Okay, brains and design.
Right. The sources define a qualified person as someone who possesses a recognized degree, certificate, or professional standing. Or, someone who has extensive knowledge, training, and experience.
So they have the formal education or the extreme specific experience.
Exactly. They have successfully demonstrated their ability to solve mathematical and structural problems related to the subject matter.
Okay, so the qualified person is essentially the architect of the scaffold.
Precisely. The qualified person designs the scaffold. They sit down and calculate the maximum intended loads. They determine the structural requirements, the necessary bracing, the material yield strengths.
Is doing the math.
Yeah, lots of math. They are also responsible for designing the training curriculum for the employees regarding scaffold hazards. They operate in the realm of blueprints, mathematics, and structural theory.
Brains, blueprints, and math. That makes sense. So where does the competent person fit into this hierarchy then?
Well, if the qualified person is about brains and math, the competent person is about eyes and authority on the ground.
Eyes and authority. I like that.
The official definition of a competent person is someone who is capable of identifying existing and predictable hazards in the surroundings or working conditions. And this is the crucial operative clause here, who has the authorization to take prompt corrective measures to eliminate those hazards.
Wait, authorization to take prompt corrective measures? That implies a significant amount of operational power.
It's massive.
They aren't just an advisor, they can actually pull the emergency brake.
They have total power over the safety of that specific operation. The competent person supervises the actual erection, dismantling, moving, or alteration of the scaffold.
Right.
They perform the mandatory daily pre-shift inspections. They are the ones who assess the physical environment, looking at the soil conditions, feeling the wind speed, watching the storm clouds.
Seeing if it's actually safe to work that day.
Exactly. They determine if the weather allows for safe work. They select the workers and direct their activities based on the daily conditions.
Let me paint a scenario to make sure I have this distinction completely locked in. Let's say a company is constructing a massive supported scaffold for a 10-story masonry project.
Okay, standard big job.
Right. The qualified person is sitting in the job trailer or a corporate office. They have their calculator out, cross-referencing the weight of a pallet of cinder blocks, the weight of the wet mortar tubs, and the average weight of a 5-man crew.
Yep, doing the load math.
Right. They draw up the schematics and say, mathematically, this structure will hold. But the competent person is the individual standing in the mud on a Tuesday morning at 6 a.m.
Exactly. In the mud.
They are inspecting the delivery of the actual steel frames off the back of a flatbed truck, and they notice that one of the vital uprights has a visible bend or maybe a cracked weld.
Right, something the qualified person couldn't possibly see from the office.
Yes, the competent person is the one with the authority to point at that piece of metal and yell, "Stop, we cannot use this. Send it back."
That illustrates the relationship perfectly. The qualified person ensures the scaffold can be built safely in theory. The competent person ensures the scaffold is built safely in reality, and that it stays safe every single hour of every single shift.
Okay, that makes it so much clearer. So what about the scaffold engineer?
Right, to complete the triad, we have the scaffold engineer. An engineer is specifically mandated for highly complex or non-standard designs.
Like what kind of designs?
For instance, designing complex mobile scaffolds or supported scaffolds that exceed usual height dimensions, often anything over 125 feet, though local codes can dictate the exact thresholds.
Oh, wow. Okay, so for the exam, engineer for complex, non-standard, or mobile designs. Qualified for standard structural design and load math. Competent for daily inspection, hazard identification, and authoritative control on the ground.
You've got it. That's exactly right.
Brains and math for qualified, eyes and authority for competent. I definitely won't forget that now.
Good, because it will definitely be on the test.
I bet. And since the qualified person has to do a massive amount of mathematical calculation to ensure the structure won't collapse under the weight of those cinder blocks, we need to dive into the strict physical construction rules.
Oh, absolutely.
Because the ASP and CSP exams aggressively test these specific measurements and ratios.
And they test them aggressively because these numbers dictate the literal margin between a routine day of work and a catastrophic multi-fatality collapse.
Yeah, the stakes are that high.
Yeah.
So what is the baseline math here?
The foundational mathematical rule of scaffolding is load capacity. The regulations dictate that a scaffold and its components must be capable of supporting, without failure, its own weight, which we call the dead load.
Right, the weight of the metal and wood itself.
Exactly. Its own weight plus at least 4 times the maximum intended load applied or transmitted to it.
Wait, 4 times? That is a massive safety factor.
It is huge.
So if the qualified person calculates that the workers, tools, and bricks will weigh 1,000 pounds, the scaffold has to be engineered to hold its own weight plus 4,000 pounds.
Yes. And understanding why that 4x multiplier exists requires looking at the physics of a job site. That multiplier accounts for dynamic forces.
Dynamic meaning movement.
Right. Job sites are not static environments where weight is placed gently and evenly. Imagine a forklift operator dropping a heavy pallet of masonry onto the platform slightly too fast.
Okay, let's visualize that in slow motion. When that pallet drops even just a few inches, you aren't just dealing with the static weight of the bricks anymore. You are dealing with mass multiplied by velocity.
Exactly. Kinetic energy.
That impact creates a shock wave of kinetic energy that hits the decking, transfers into the transoms, travels down the upright standards, and punches into the base plates.
Yes, the force travels all the way down.
So a static load of 1,000 pounds might momentarily exert a dynamic force of 2,000 or 3,000 pounds upon impact.
Precisely. The 4x safety factor absorbs that kinetic impact. It absorbs the lateral wind shear that constantly pushes against the side of the structure.
Wow, wind too.
Yeah. And it accounts for the microscopic structural fatigue of the metal over time. And frankly, it accounts for the unfortunate human reality that workers frequently and dangerously underestimate how much weight they are loading onto a platform.
They just keep stacking bricks.
They do. Now, that is for supported scaffolds. If we are dealing with the suspension ropes or wires on a suspended scaffold, the ones hanging down the exterior of the building,
Like our window washers.
right, those ropes must be capable of supporting 6 times the maximum intended load.
6 times for the ropes.
Wow.
Because if a supported scaffold fails, the cross braces might buckle, the frame might crumple, but there is some resistance before total collapse. You have a second to react.
Right, it doesn't always go instantly.
But if a suspension rope snaps, there is zero redundancy. It's an immediate, catastrophic freefall.
The severity of the consequence dictates a much higher engineering safety factor, 6 times. Additionally, the minimum capacity for any scaffold platform, regardless of its use, is 75 pounds per square foot.
Okay, 75 pounds per square foot is a baseline. So we have the mathematical foundation for the weight. But what about the height?
Height is crucial.
Because I see these structures towering over city streets, sometimes reaching dozens of stories into the air. How tall can you build a freestanding tower before it becomes top-heavy and just tips over?
The primary rule governing height stability is the 4-to-1 ratio.
4 to 1.
Yes. The height of the scaffold cannot exceed 4 times its minimum base dimension.
Okay, give me an example.
Let's say your scaffold base is 5 feet wide. You can only build that scaffold 20 feet high as a completely freestanding structure.
Right, 5 times 4 is 20. That feels like a direct application of center of gravity physics.
It absolutely is.
Because if the base is narrow relative to the height, the structure becomes highly susceptible to tipping moments, like a gust of wind, a heavy cart rolling to the far edge of the platform, or even just a worker leaning out over the guardrail.
Any of that will shift the center of gravity outside the physical footprint of the base.
And once that center of mass crosses the vertical plane of the outermost leg, gravity takes over and the whole thing comes down.
Yes. If we connect this to the bigger picture of site logistics, you often need to go much higher than 20 feet on a 5-foot base.
Yeah, buildings are way taller than 20 feet.
Right. So when you exceed that 4-to-1 ratio, the scaffold must be restrained from tipping by guys, ties, or braces that secure the scaffold directly to the permanent building structure.
Oh, so you essentially anchor the temporary puzzle into the permanent architecture.
Exactly. You tie it into the wall.
Are there specific intervals for how often you have to tie it in? You can't just throw one strap at the very top, right?
No, the regulations are highly specific about this. You must tie and brace the scaffold at intervals not exceeding 30 feet horizontally and 26 feet vertically.
30 horizontal, 26 vertical.
Right. You are creating a mathematically proven, secure grid. These ties act in tension and compression to prevent the slender steel columns from buckling outward or bowing inward under the immense vertical loads.
All right, so we have a structure that is mathematically engineered to hold 4 times the expected weight. And it's tied securely into the building every 30 feet across and 26 feet up.
Yes. The frame is solid.
Now we have to actually build the deck, the floor where the workers will actually stand. I was reviewing the source material, and the rules governing how you lay down the wooden planks are incredibly granular.
They have to be granular. Bad planking giving way is one of the leading causes of falls on a job site.
Really. Just bad wood placement.
Yes. First, the platform must be fully planked or decked. You cannot have missing planks that create voids.
Obviously.
And between those individual planks, there can be no more than a 1-inch gap.
Wait, why a 1-inch gap specifically? Why not 2 inches or 3?
Well, because anything larger than an inch fundamentally changes the hazard profile. A 2-inch gap becomes a severe tripping hazard for the toe of a work boot.
Oh, catching your toe up there would be terrifying.
Exactly. But more importantly, it creates a void large enough for hand tools, bolts, or debris to fall through to the levels below.
Protecting the guys underneath.
Right. The platform itself must also be at least 18 inches wide, providing a worker enough physical space to stand, pivot, and operate equipment without constantly balancing on a narrow precipice.
Okay, 18 inches wide at minimum. But how do they handle the ends of the planks where they meet? You obviously can't have them just floating over open space.
No, definitely not. Each abutted end of a plank, where one plank meets another end-to-end in a straight line, must rest securely on a separate support surface.
Okay, abutted ends must have their own support.
Right. But if the planks are overlapping instead of abutting, they must overlap by at least 12 inches over a support, unless they are nailed or physically restrained to prevent movement.
So a full foot of overlap.
Yes. Furthermore, the end of a platform must extend at least 6 inches over its support, unless it's cleated or restrained by hooks.
Okay, I saw this rule about a 6-inch overhang, and initially thought it had to be a typo or like an overregulation.
A lot of people think that at first.
Yeah. Because why would you intentionally want a piece of wood hanging out into thin air past the support beam where someone can step on it?
Walk through the physics of what happens if that overhang isn't there. If a plank only overhangs the support bar by a single inch, and a heavy worker steps down hard on that very edge, the plank acts exactly like a seesaw.
Oh, I see it now.
Yeah.
The support beam acts as the fulcrum. The worker steps on the short 1-inch end. The opposite end of the heavy plank flips up violently. The worker's end dips down. The entire plank slips off the support beam, and the worker falls straight through the deck.
Exactly. That minimum 6-inch overhang ensures there's enough cantilevered weight and surface friction resting on the support to prevent the plank from pivoting upward and slipping off the frame when point-loaded at the edge.
It's literally the physics of a playground seesaw applied to life-or-death construction scenarios.
It really is.
But out of all these specific dimensions, the 18-inch width, the 12-inch overlap, the 6-inch overhang, there was one particular rule in the text that created an incredible aha moment for me.
Oh, which one?
It's the absolute prohibition on painting wood platforms.
Ah, yes. The paint rule.
Yeah. At first glance, someone might think, who cares if the wood is painted? Maybe the contractor wants it to match their company colors.
Right, aesthetics.
But then you realize what paint actually does. It's like buying a used car with a fresh, suspiciously cheap paint job. You
Yes.
instantly have to wonder what rust they're hiding.
Exactly.
Because opaque paint hides the grain. It hides the stress cracks. It hides the dry rot and the structural degradation of the wood.
That analogy hits the nail on the head. Think back to our competent person performing their mandatory daily morning inspection.
Right, the guy in the mud at 6 a.m.
Exactly. They are walking the deck looking for hazards. They cannot see microfractures, moisture rot, or termite damage through a thick layer of yellow enamel paint.
They are blind to the structural integrity.
A painted scaffold plank is fundamentally an uninspectable scaffold plank. And in the world of safety, an uninspectable component is automatically classified as a deadly hazard. It must be immediately removed from service.
So let's step into the boots of that competent person for a moment. We arrive on site at 6 a.m. We know what to look for on the decking. But what is the mental checklist we are running through to inspect the very foundation of this massive structure before we even let anyone climb the first ladder?
The inspection always starts at the ground and works its way up.
Yeah.
First, is the ground itself stable and level?
The actual dirt.
Yes. Are we building on properly compacted dirt, or is it soft, saturated mud after a night of heavy rain? Scaffold poles, legs, frames, and uprights must sit on metal base plates.
Right.
And those base plates must sit on mud sills or another adequate, firm foundation.
A mud sill. That's essentially a piece of heavy, sturdy timber placed flat on the ground directly under the metal base plate, right?
Exactly.
What is the physical mechanism of a mud sill? Why is it so important?
Its function is load distribution. It takes the immense pinpoint load traveling down the narrow metal leg of the scaffold and spreads that kinetic energy over a much wider surface area of the ground. It prevents the scaffold leg from punching deep into the earth, much like how a snowshoe prevents you from sinking into deep snow, whereas a stiletto heel would punch right through.
That is a brilliant way to picture it. The snowshoe versus the stiletto. Because if one leg sinks even a few inches into soft soil, the entire scaffold goes out of plumb.
It leans.
And then the center of gravity shifts dramatically, and you risk a total structural collapse.
This is why the competent person meticulously checks the mud sills. They check that the base plates are securely centered on them.
What if it's on wheels?
If it's a mobile scaffold, they verify that every single caster wheel is locked, and that the diagonal cross braces are tight, undamaged, and perfectly plumb. They verify the 4-to-1 height ratio is respected, or that the wall ties are tightly secured to the building.
So we verified the soil, we built this mathematically perfect structure that can hold 4 times its load. The planks are unpainted, properly overlapped, and overhanging the supports.
It's totally solid.
We have essentially constructed an unyielding fortress of a platform.
Yeah.
But that perfectly engineered deck doesn't matter at all if a worker gets dizzy, loses their balance, and simply steps off the edge.
No, it doesn't. Gravity always wins.
How does the safety system adapt to the unpredictable, vulnerable nature of human balance?
Well, this is where we pivot from ensuring the structural integrity of the scaffold to implementing active fall protection for the worker.
Okay.
The cardinal rule here, which is heavily and consistently tested on the ASP, is the 10-foot rule.
10 feet.
Yes. Guardrails or personal fall arrest systems, PFAS, are explicitly required when an employee is working more than 10 feet above a lower level on a scaffold.
I really need to highlight this because this is a classic deliberate trip up on these exams.
Oh, they love testing this.
Yeah. 10 feet is the trigger for scaffolding.
Okay.
But in general industry standards, fall protection triggers at just 4 feet. And for steel erection activities, the trigger leaps all the way up to 15 feet. A safety professional really has to compartmentalize these numbers based on the specific operational task being performed.
Compartmentalization is essential. For scaffolding operations, 10 feet is the absolute legal threshold.
10 feet, period.
Period. If a worker is standing at 10.5 feet on a scaffold without a compliant guardrail system or a properly anchored harness, that is a severe, highly citable OSHA violation. Unprotected sides and edges remain one of the most frequently cited serious OSHA violations across the entire industry.
Let's break down the primary method of fall prevention then. The physical guardrail. What are the specific dimensions and mechanics a safety professional needs to verify when inspecting a guardrail?
A standard compliant scaffolding guardrail system requires a top rail that must be installed strictly between 38 and 45 inches above the platform surface.
38 to 45 inches. That places the rail roughly waist to chest high for the average adult.
Exactly. That specific height range is engineered based on the human center of mass. It has to be high enough to prevent a worker from flipping over the top of it if they trip and fall forward.
Like flipping over a low fence?
Right. But it must be low enough to effectively intercept their center of gravity before their momentum carries them over.
That makes perfect sense.
And it cannot solely be a top rail. There must be a mid-rail installed approximately halfway between the top rail and the platform deck.
What's the mid-rail doing? Just extra strength?
No, this mid-rail prevents a worker from slipping underneath the top rail if they fall backward or, if they are working on their knees and slip.
Ah, okay. So the top rail stops you from going over and the mid-rail stops you from sliding under.
Exactly.
But earlier we talked about the Focus 4 hazards, and one of them is being struck by falling objects.
Yes, struck by.
If I'm a worker on the ground, walking under a scaffold, a guardrail that is 40 inches in the air does absolutely nothing to stop a heavy steel wrench from rolling off the deck and hitting me in the head.
No, it doesn't do a thing for that.
So how do the regulations engineer a solution for gravity, acting on tools and debris?
The sources explicitly address falling object protection with specific, testable engineering controls. To protect employees working below, you must erect physical barricades on the ground to entirely restrict access to the hazard area beneath the scaffold.
They'll just keep people away entirely.
That's the first line of defense. But more importantly, up on the scaffold deck itself, you must install tow boards along the unprotected edges of the platforms.
A tow board. That's essentially a solid, continuous lip running along the very bottom edge of the platform deck.
Yes, typically constructed of 2x4-inch lumber or an equivalent solid material. It is a critical safety barrier.
So it's like a tiny wall for tools.
Exactly. If a worker trips and kicks a heavy pneumatic nail gun or drops a 15-pound box of lag bolts, the tow board physically intercepts that material. It prevents it from rolling off the edge into free space.
Which is huge.
Oh, massive. If we connect this to the bigger picture of physics, a dropped tool from 20 feet up accelerates rapidly due to gravity. By the time that wrench reaches the ground level, it possesses enough kinetic energy to be fatal, even if the worker below is wearing a hard hat.
It's like a bullet at that point.
It really is. The regulations also mention secondary controls like deploying debris nets, catch platforms, canopy structures, and strictly mandating hard hats for anyone in the vicinity. But preventing the object from ever leaving the deck in the first place using a solid tow board is the primary, most effective engineering control.
So we have guardrails to catch the humans and tow boards to catch the tools. But what about scenarios where a guardrail simply isn't feasible?
Like when?
Like on a suspended scaffold where workers are hanging on the exterior glass of a building. They can't really have a full guardrail in the way of the work. They're required to use a personal fall arrest system, right? A harness and a lanyard?
Correct. PFAS.
And there was a specific detail in the text regarding the anchors for these systems that left me genuinely confused.
Okay, let's hear it.
The rule states that the PFAS anchors must be completely independent of the scaffold support system.
Yes, they must be independent.
Wait, if the anchor has to be independent of the scaffold, doesn't that make things incredibly difficult on a job site? I mean, the worker has to find a completely separate structural beam on the building to tie their lanyard to, all while standing on a moving scaffold.
It does make the logistical operations significantly more complex. It requires more planning, more equipment, and more time.
It sounds like a headache.
It can be.
Mhm.
But if we connect this to the bigger picture, the grim reality of structural failure makes this independent anchor rule absolutely absolute. Let's walk through a visualization.
Okay, set up the scene.
Imagine you are working on a suspended scaffold hanging 30 stories up on the side of a skyscraper. Your fall arrest lanyard is tied directly to the guardrail of the scaffold you are standing on.
Okay, I'm tied to the scaffold.
Suddenly, the primary suspension rope snaps.
Oh, if the primary rope snaps, the scaffold falls.
Well,
And if I'm tied to the scaffold, I see it now.
if the scaffold falls and you are tied to the scaffold, you are going down with the ship.
You're just riding the debris down.
Exactly. Your harness won't save you. It will simply ensure you remain tethered to tons of collapsing steel and wood as it plummets to the ground.
That is terrifying.
By explicitly mandating that the personal fall arrest system is anchored to an independent structural member of the building itself, OSHA ensures that if the scaffold completely fails and drops away beneath your feet, you will simply be left suspended safely in midair by your independent lifeline, waiting for rescue.
Left hanging from the building itself.
Right. Independent anchoring is an absolutely non-negotiable requirement for survival in catastrophic failure scenarios.
Going down with the ship, that is a terrifying, vivid visualization.
Right.
And it perfectly explains why the regulation is written with such strict language.
It's meant to save lives in the worst-case scenario.
It really highlights the old industry saying that every single OSHA rule is written in blood. Someone, somewhere, tied off to the scaffold failed, and they didn't survive. So now the rule is independent anchors only, no exceptions.
Sadly, yes. The regulations are heavily codified lessons learned from decades of past tragedies.
So we have the architecture down. We understand the math of the load capacity. We have the physical guards, the tow boards, and the independent lifelines.
The physical setup is secure.
But physical guards and perfect math are entirely useless if the workers themselves are acting recklessly or making uneducated decisions on the deck.
That is the wild card, human behavior.
Right. A perfect scaffold cannot save a worker who bypasses every safety protocol. This transitions us into the final major area of our QHSE talks the human element. Because managing operations, movement, and training is where safety theories meet the messy reality of human behavior.
That is the fundamental truth of safety management. It is never just about building a structure. It is a continuous, relentless educational and behavioral effort.
It's an ongoing battle.
And nowhere is that friction more apparent than in the rules governing the movement of scaffolds.
Moving them. Okay.
Often you have a mobile scaffold built on caster wheels, and the workers need to move 10 feet down a wall to continue painting or running conduit.
I can see where this is going.
The overwhelming human temptation is to save time. The workers want to stay up on the platform while someone on the ground pushes the scaffold to the next spot.
I've literally seen it happen.
Yeah.
It essentially turns a towering metal structure into a giant, incredibly dangerous skateboard.
That's exactly what it is, and the danger is rooted in physics. The dynamic forces of rolling a tall structure completely change its stability profile.
Okay, so what do the regulations say about riding it?
According to the text, employees absolutely cannot ride a moving scaffold unless a very strict, highly restrictive set of criteria are met simultaneously.
What are the criteria?
First, the ground surface must be within 3 degrees of level and completely free of pits, holes, or obstructions.
So basically, perfectly flat concrete.
Yes. Second, and this is the most critical structural change, the height-to-base ratio is no longer the standard 4:1. It shrinks dramatically to 2:1.
Wait, 2-to-1. So if the base is 5 feet wide, it can only be 10 feet tall if you want to move it with humans riding on it.
That is correct. Half the height.
Why such a massive reduction in the allowable height? What changes so drastically when you add wheels?
It comes down to kinetic energy, momentum, and inertia. When a worker on the ground pushes a scaffold, the wheels at the base move forward immediately.
Right, they start rolling.
But the mass of the workers and materials sitting at the top of the tower wants to stay at rest due to inertia.
Oh, because it hasn't caught up yet.
Exactly. This creates a lagging effect at the top, inducing a severe tipping moment. The base moves out from under the top.
Like pulling a rug out from under someone.
Yes. And conversely, when the person pushing stops, the wheels stop immediately, but the mass at the top wants to keep moving forward.
Jerk forward.
Right. A 4:1 tower is highly susceptible to a whipping action that will tip it over under those dynamic start and stop forces. By reducing the ratio to 2:1, you lower the center of gravity so significantly that the structure can safely handle those kinetic forces without tipping.
That is wild.
Furthermore, outriggers must be installed on both sides to widen the footprint. A competent person must be present to actively supervise the movement, and the employees riding on board must stay strictly on the portion of the scaffold that is directly inside the footprint of the wheels.
Wow, that is a fascinating application of physics. The laws of momentum completely dictate the safety policy.
They do. You can't argue with physics.
You really can't. And speaking of external forces impacting safety, the sources also dedicate significant attention to weather constraints. You mentioned earlier the competent person's duty to monitor the sky. How strictly does weather govern scaffold operations?
Very strictly. Workers are explicitly prohibited from working on scaffolds covered with snow, ice, or other slippery materials, except for the specific, necessary task of clearing those materials off the deck.
Which makes sense. You can't have a slippery deck.
Right. Moreover, work is entirely prohibited during storms or high winds unless the competent person determines it is safe to proceed, and the employees are actively protected by a personal fall arrest system or physical windscreens.
I noticed a very specific caveat about windscreens in the text.
Yeah.
You can't just wrap a scaffold in plastic to block the wind, right?
No, that is a vital caveat. Windscreens cannot be used unless the scaffold is engineered and secured against the anticipated wind forces.
Because it catches the wind.
Exactly. If you wrap a tall scaffold in thick tarps to block the winter wind, you have just inadvertently created a massive, highly effective sail.
A sail? Oh my gosh.
If that scaffold isn't heavily tied into the building structure with additional anchors, a strong gust of wind will catch that screen and generate enough lateral force to blow the entire scaffold over, pulling the anchors right out of the wall.
It's all interconnected.
Yeah.
Every single intervention, like adding a tarp to keep workers warm, creates a new hazard variable that must be mathematically accounted for.
Every single change matters.
Now, what about the simple act of just getting on and off the deck? Access. I know I've seen workers treating the X-shaped diagonal cross braces on the side of a scaffold frame like a convenient ladder.
We all have, and that is a classic, highly dangerous, and highly citable violation.
You can't climb the braces.
No, the regulations are unambiguous. Safe access must be formally provided if there is no existing access, like a building window or an adjacent floor within 2 feet above or below the platform.
Okay, so you have to provide something specific.
Yes. This means the employer must provide attachable ladders, integrated stair towers, or ramps. Climbing the cross bracing is strictly prohibited.
Why is it so dangerous to climb the braces? They look strong enough.
Those braces are engineered solely for lateral structural stability. They are not designed to support the concentrated point load of a human foot, and they do not provide proper ergonomic handholds.
So they could bend or you could just slip.
Exactly. A competent person seeing a worker climbing a cross brace must immediately halt the behavior.
Okay, let's unpack this. So what does this all mean for the safety professional, preparing for these exams or managing a site?
It means a lot of responsibility.
It means that the ASP and CSP exams aren't just testing your rote memorization of inches, pounds, and ratios. They are testing your deep understanding of how to govern human behavior in highly dangerous, dynamically shifting environments.
That's the core of the job.
You have to know the specific rules, yes, but you also have to deeply understand why the rules exist, the physics, the psychology, the hazards, so you can train the workers effectively.
The training requirements outlined in Subpart L reflect exactly that need for comprehensive understanding. The employer must ensure that every single employee who works on a scaffold is formally trained by a qualified person.
By the qualified person, the architect.
Right. They must be taught to recognize electrical hazards, understanding the lethal danger of conductive metal scaffolds near overhead power lines.
Oh, because the whole thing is basically a giant lightning rod.
Exactly. They must intimately understand fall hazards, falling object hazards, how to properly distribute materials so they don't overload the decking. And they must know the mathematical load-carrying capacities of the specific scaffold they're using.
And I imagine this training isn't just like a 15-minute video you watch on your first day and never think about again.
It cannot be. Retraining is legally mandated whenever an employer has reason to believe an employee lacks the skill or understanding needed for safe work.
So if someone messes up,
Yes. If the competent person is walking the site and sees someone climbing the cross braces or overloading a deck with masonry, that worker needs immediate retraining.
stop work. Go get trained.
Yes. Furthermore, retraining is required if the worksite conditions change or if a new type of scaffold or fall protection system is introduced. Safety is an ongoing daily dialogue, not a static certificate you hang on the wall.
That brings us to the end of our comprehensive look at this vital topic. We've covered a massive amount of technical and operational ground today.
We really have. It's a lot to take in.
For everyone listening who is prepping for their exam or heading out to the site tomorrow, let's do a rapid-fire recap of the absolute most vital takeaways from ASP 11 Domain 2, Topic 8, Part G.
Sounds good. Let's review.
First, the math and forces. A scaffold must be engineered to support its own weight, plus 4 times the maximum intended load, accounting for dynamic impacts.
Right, the 4x multiplier.
Suspension ropes face even stricter rules, requiring them to support 6 times the intended load due to the catastrophic nature of a failure.
Exactly. 6 times for ropes.
Second, the structural dimensions. Height cannot exceed 4 times the minimum base dimension, the standard 4-to-1 ratio.
Unless you are moving it.
Right. But if you want to move that scaffold with people on it, the physics of momentum demand that ratio drops to 2 to 1.
Half the height.
Planks must have no more than a 1-inch gap to prevent falling tools, must overlap by at least 12 inches, must overhang their supports by a minimum of 6 inches to prevent the seesaw effect, and must be at least 18 inches wide.
Good memory.
And absolutely no paint on wood platforms, because paint hides the fatal flaws.
Never paint the planks.
Third, the human hierarchy. The qualified person uses their degree, brains, and math to design the scaffold and calculate the loads.
The architect.
The competent person uses their trained eyes and operational authority to inspect the scaffold daily, monitor the weather, and stop work immediately if hazards arise.
The authority in the mud.
And finally, the fall protection. The magic number for scaffolding fall protection is 10 feet.
Always 10 feet.
Once you hit 10 feet, you need guardrails between 38 and 45 inches high, equipped with mid-rails and toe boards to intercept falling objects.
Right.
If you rely on a personal harness on a suspended scaffold, your anchor must be entirely independent of the scaffold structure, ensuring you don't go down with the ship if it fails.
That is an excellent synthesis of the material. You've distilled the technical and operational essence of OSHA Subpart L flawlessly.
Thanks. I think it's vital to have it crystal clear.
But I want to leave you, the listener, with a final lingering thought to ponder as you continue your studies or as you walk your job site tomorrow morning.
Okay, let's hear it.
We have engineered scaffolds to mathematically support massive dynamic loads. We have written precise regulations governing every single inch of planking, overlapping, and guardrail height based on the laws of physics.
We all the rules.
Right. But as safety professionals, how do we engineer a human work culture that is as robust, deeply rooted, and fail-proof as the steel frames we are erecting?
That's the million-dollar question.
Because the ultimate challenge isn't just bolting together a safe scaffold. It's building a safety mindset within your crew that never accepts a painted plank, never ignores a bent steel frame, and never ever takes a shortcut to save a few minutes.
That is the real puzzle, isn't it? Treating the culture with the same exact precision and rigor as the architecture.
It has to be treated the same way.
Remember earlier we talked about scaffolds being temporary modular puzzles rather than permanent architecture?
Yeah.
Well, your safety culture is the permanent architecture.
Beautifully said.
It has to outlast every temporary structure you ever build, and it has to protect every worker long after the steel is dismantled.
Absolutely.
Thank you for joining us for this edition of QHSE Talks. Stay curious, stay rigorous, stay safe, and go apply this knowledge on your sites and absolutely crush your exams. We'll talk to you next time.